Doug Ramsey is the only person who did not provide a biography, and so when I mentioned this to him, he said, well, feel free to make it up. So Doug Ramsey is a native of Tajikistan, and he is currently serving as that nation's ambassador to Latvia. And okay, Doug is actually one of the greatest assets to the College of Natural Resources. Doug is a professor in the Wildland Resources Department here at Utah State. And one of the things that's really helpful is he is both a geographer and a range scientist. And so that means he can put on more hats. It means he has to say yes to more things. But it also helps. It brings an expertise that I think is really going to be useful to us. And so I'm going to let him come up here and tell us about Sagebrush Steppe Ecological Site Classification.
Hi. The work I'm going to present to you today is of course, not my complete work. Actually, the majority of it is not my work. It's the work of my graduate students, Kate Peterson and Alex Hernandez. Kate comes from recently from Oregon, where she has worked with BLM, developing ecological site descriptions. Alex comes from Honduras, another semi-arid landscape. And he's actually working in Box Elder County, but also applying his expertise to Rich County. Kate is focused specifically on Rich County, and I'll show you what they've been trying to do. Now, this is a token, what is an ecological site slide. Everybody should have one of these in an ecological site presentation. And we're probably all familiar with what it is, a distinctive kind of land with specific physical characteristics that differs from other kinds of land in its ability to produce a distinctive kind and amount of vegetation. And some people, I think, are starting to modify this a little bit, but that's basically what's been published in the National Soil Survey Handbook. Now, our original objective for Rich County, and what we were contracted to do by the NRCS, was to, and I'm sorry for the shadowing, I didn't put that there, it just kind of appeared, is to develop state and transition models for each ecological site description in Rich County, or the MLRAs, which are three MLRAs, three major ones that intersect Rich County. Our job was to develop the state and transition models, which is being done by Neil West and Lisa Lang-Stoner, who's assisting him. But we ran into a snag when we were doing this. The snag was that a lot of the ESDs in Rich County weren't as well correlated as they should be, mostly because the Rich County Soil Survey is an older survey, and they converted, they started out with range sites and then tried to fit as best they could existing ESDs. And a lot of the ESDs, or maybe not a lot, some of them, especially some of the Sagebrush ESDs, oops, wrong pick, I did it again, were taken from other MLRAs and fit into that soil mapping as best as they could, because there was no other information to go from. So the past year or so, we've been working with the NRCS to re-correlate some of these sites by taking ESDs from Wyoming. I think this is, reassigning ESDs. We're borrowing some ESDs from Wyoming and rewriting them a little bit to fit within our landscape. So better stretch to pull from Wyoming than from the Uinta Basin up. And once we do that, we hope to, of course, finish all of the state and transition models for Rich County. But at the same time, we need to correlate the ESDs. So we're doing two things simultaneously. And one way we've decided to do this is what Kate's been doing. And that's two things. Kate and Lisa Lang-Stoner have been trying to reassign these ESDs to soil map units using what we're calling a paper correlation, just basically looking at the write-up and comparing it to soil map unit characteristics and matching it that way. But also, what Kate's been doing is trying to model the distribution of potential key plants within Rich County in order to help with the correlation. And that's what we're going to, part of what I'm going to present right now. This is a flow chart which basically describes the different variables, the different forces in action that determines to a large degree what plants grow where. These events down here are basically disturbance events, which we're not paying attention to. We're trying to look at potential distribution and not actual distribution. And the goal is to develop spatial data layers, GIS data layers, that describe these different variables across the landscape, so we can get a spatial distribution of key plants. So we have a set of data layers that Kate's put together. A lot of it is interpreted from digital elevation models, geology, climate maps. There's some remote sensing data here, but not very much. We're trying to get at the potential. But basically, we're taking these basic variables, reinterpreting them into different data layers, and generating, in this case, logistic models to identify where plants should be. So the idea here, and this, the idea here is to model these plants. I thought this was separated before. I forgot to put them all together. So we have different species occurring potentially in different areas, and then overlay with that the soil survey map to help us identify where these ESDs, which are associated with these key species, should be. Of course, we can't model all the species. We need a lot of field data to do that with, and some species are so general that they occur everywhere. Some species are so specific that you really can't get a good enough sample to model those. So we're just picking out as many of the major species as we can, and I'll show you about 5 of those. First, we need to develop a sampling strategy. And to do that, these data layers were merged in a classification type of approach into one data layer with 25 different unique clusters. It didn't really matter what those clusters represented on the ground. We can start matching those. What was important is that these clusters represented unique areas on the landscape that are representative of those variables that we have above. And then sample each one of these as best we can to get a fairly decent representation of the variability within a county as described by those variables up above. In this case, this summer Kate collected over 200 field sites, I think about 240 field sites, and used those, or portions of those, for the modeling effort. The subsequent analysis actually took additional field data from the Southwest Gap. We collected earlier about 800 field sites in Rich County to try to get a sense of the accuracy. This is the result for, in this case, black sage. The purplish areas are where Kate predicted black sage would occur using a logistic regression. This is basically taking logistic continuous probability and breaking it at some threshold, and that threshold basically defines where it is and where it's not. And in this case, she identified a 0.5 probability threshold, generated an accuracy assessment. It was this accuracy is basically where the model and the Southwest Gap field data points agree that this plant occurred, and it's about 30%. Not that good. It increases a little bit as that threshold is manipulated left or right to find a more natural break instead of just a random 50%. The overall accuracy, if you look at where it's not versus where it is, it's about 77. So if you look at that, it's not too bad. But if we're trying to predict where it is, then we're only about 30% accurate right now, and maybe 46% if we're a little bit more generous with our breaks. And actually, as we look at these maps, the distribution of points seems to be fairly well represented. This is where we usually find black sage in Rich County. And we're not sure exactly why the accuracy is so low, because the picture looks good. It should be accurate. But it may be that there's so much salt and pepper here in these areas that it's really difficult to get a decent accuracy, especially if you're drilling a point down. You're bound to miss if you're slightly off. Mountain big sage. Better predictive ability with this one, about 56 to 60%. And it seems like it's occurring where it should occur, in the slightly higher elevations. It is falling potentially within these agricultural areas here too, which we need to look at. Those are more moist environments, so that's probably why it's landing there. But this is a potential distribution of mountain big sage. This is Wyomingensis, and in this case it's threshold a little bit more. It broke up into 2 or 3 categories. But just looking at where it is, we're about the same as mountain big sage. But it's occurring approximately where we would expect Wyomingensis to occur, and hopefully. And actually, we're trying to do this right now, overlay the soil maps to see if the soil mappiness actually jive with the map, and we can use this to help us identify where these ESDs belong. There's a graph for blue bunch wheatgrass, its potential distribution and its potential accuracy, and western wheatgrass, which is pretty broad in its distribution, but interestingly enough, the accuracy is fairly low, especially for the presence. With so much there, we expect that the presence accuracy to be a little bit higher, but it's a little bit lower. And grass is, of course, a little bit tougher than shrubs and or trees. We haven't done trees yet. So if we merge all these together and intersect them with the soil mappiness, we can get an idea, or at least an indication of where we can help correlate these ESDs to that we have from different areas other than the state, other than this county. Okay, the other work that we're doing, it dovetails with this. It's more of a current vegetation. Kate's work is a potential distribution and a correlation of ESDs. What Alex is doing is trying to model the actual distribution of plants using image processing, remote sensing data, so we can get an idea of what the transitions have been over time from what ESD says it should be and what is actually there. So basically, we want to try to model continuous vegetation fields, which is a term that remote sensors use to basically identify percent cover, aerial cover, not canopy cover, aerial cover of different life forms. And we're looking at shrubs, trees, herbaceous species, and bare ground. Those are the 4 basic dependent variables that we're trying to model out. Try to match that with land cover maps and use that as a help to model these maps, and basically use existing imagery. In this case, Landsat thematic mapper imagery to do this with, because it's a fairly decent scale to do this kind of analysis, and match it up with higher level remote sensing, similar to the NAPE, if you're familiar with that, the National Agriculture Imagery Program data, which is a 1 meter data set, 1 meter remote sensing data set of the entire state. We have statewide coverage in natural color area photographs with NAPE and color infrared photographs. And for a lot of urban areas, we have 1 foot data now. If you're working close to an urban area, you might be able to get 1 foot imagery. Okay, so in order to do this, we have to train the data set. There's always training involved. We can't just guess at it. And to do this, we've also employed the Southwest REGAP field data sets, and in this case, 923 observations across the landscape. Actually, we did use a NAPE imagery to help collect more tree points, because there are very few tree points in the GAP database, so we supplemented those. Use Landsat imagery and also convert those to some vegetation indices, some topographic variables, and the Southwest REGAP land cover class to help restrict the models. So we're using a cubist type of approach. It's a regression tree approach. And we threw this Southwest Redact land cover class there to basically say if I'm in Sagebrush, I will have a different model. If I'm in Juniper, I'll have a different model, and so forth, so that we can fine-tune this modeling effort. And as far as the accuracy assessment, we basically withheld points to look at how well the model was working. Not a true accuracy assessment, just a validation of the models. Like I said, we ran Cubus. Cubus is a program developed by can't remember the company name in Australia. It's a small company. All they do is focus on regression and classification and regression trees. And basically, regression trees are becoming the tool of choice for a lot of remote sensors because you can throw a bunch of stuff at it and get something out sort of magically. Cubus then, and it actually, I say it facetiously, but it's really kind of true. Cubus and classification trees are basically designed as an exploratory tool to help you explore your data set to understand what's going on and then develop models from that. But a lot of people now, including ourselves, are using it to basically throw all of our data at it and come up with an answer. But in doing so, we vary the independent variables that go in. We change them around to see what happens to the model. So we're still doing some data exploration to fine-tune the model itself and figure out which one works the best. Oops. Okay, this is the model we generated for bare ground. Here we have high amounts of bare ground. The darker colors, lighter colors is low. And this is basically the scatter plot of the real points versus the predicted points for all the data sets, all the points we modeled. And bare ground actually happens to be one of the best that we can model using remote sensing data, mostly because a lot of these landscapes have a lot of bare ground, and that becomes a dominant variable. So bare ground becomes important. And bare ground actually maybe becomes the most important because the reciprocal of that, of course, is not bare ground. And we can get a good idea of what total cover is just by looking at bare ground. And that happens to be a fairly decent model. If we look at the 2006 National Agricultural Imagery Program data, the NAPE imagery, and we superimpose that map, you can kind of see what the model is doing. So we have some agricultural fields, some fallow fields here, dry land, agriculture. We have areas that have been managed up here, shrublands there, juniper landscapes. And if we look at the model, the red or the purpler or the more magenta the color, the more bare ground we have on the landscape. So it seems to be working fairly well. And when we overlay this with this high resolution remote sensing, we tend to feel fairly comfortable that the bare ground model is working fairly well. The accuracy is slightly different. We grouped accuracy into classes. So the model basically identifies percent canopy cover in percentages from 1 to 100, or proportions from 0 to 1. But then we group them because doing accuracy assessment on each percentage doesn't make much sense, and you get a very poor sample, and you just can't do it that way. So we group them into, I guess, random groupings. We just picked a 10% increment and looked at how the points landed from the withdrawn points landed on the data set, and then just estimated the accuracy. And it's so. Again, for some reason, the image looks a lot better than the accuracy assessment. Looks can be deceiving, though. For trees, we did the same thing. But now, I don't know if you noticed before, the variables for bare ground just included 3 or 4 different independent variables. That's what optimized the model. Now we have to add a few more for trees. Develop our model. Look at the result, the real versus predicted, and this is not quite linear. This is a 1-to-1 line. There's a lot of points around the 0 mark. There are many trees out there. But the result is this map Low trees in, of course, the valley bottoms, we wouldn't expect it. Trees increasing as we go up the slope. And if we drape it over the same kind of imagery, you can see the juniper as a tiny specks here. And that's basically the output of the model, which looks pretty good. It's not too bad. The accuracies are just slightly better than the bare ground when we drop the points on it, but they're still maximum maybe 47% accurate. We still need to do quite a bit of work to fine-tune it and figure out why it looks good to the eye, but quantitatively it's not as good as we hope it to be. For shrubs, a different set of predictors. Again, there's not much relationship here with shrubs. It's sort of a flat distribution against that one-to-one line. That's the. But when you look at the map, the shrubs are basically occurring where the shrubs should occur, along the foothills here, and not much in the valley bottoms where it's cultivated. And if we drop the shrubs against the nape, it's kind of hard to tell. So we still need to do some work with the shrubs to figure out what the accuracy is visually. But when we look at the distribution, we're very poor at looking at the very low density shrub areas, which is common because we can't see individual shrubs within a 30-meter footprint, especially when you have 0 to 10% shrub in that 30-meter area. It's not the majority, but when it starts to build up, especially for some reason at this 21 to 30% bracket, it becomes very good. And it drops down again at the very dense ones because it's getting confused with trees in this case. So in some areas it tends to work out fairly well. Some areas it still needs a little bit of work. For forbs and grasses, 5 minutes. Thank you. For forbs and grasses, slightly better point distribution predicted versus real, but still a little bit flat and kind of tapering off. The output. It's hard to look at herbaceous sometimes. I guess if we look back at and I should have put these side by side, the potential grass model and this actually looks kind of like the distribution of western wheatgrass. The averages weren't too bad in comparison. We thought the herbaceous category would be the hardest one because it's usually the hardest one to pick out in a more sensing type of exercise. But the accuracies were higher than the other ones. And of course, it's very difficult to quantify this visually because you can't see the forbs and grasses even with the high resolution imagery. So we have to go on the grounds yet to validate this. But just a withholding of the points gives us this kind of an accuracy. Okay. So the concept here is basically to map or model the potential distribution of key individual shrubs and grasses to get a handle on where these ESDs should occur on the landscape, and then model the actual percent distribution of life forms in order to get an idea of what's happened on that landscape, over time, and compare the two and get some kind of a result of what the landscape change has been when you compare it to a potential type of map. And that's it. Are there any questions?
How old is the soil survey that you're trying to base the site descriptions on?
They predate ESDs. Shane here. I don't know. Shane, how old is that soil survey?
From the 80s.
Okay.
So are there issues with that in terms of?
There are always issues with any kind of interpretation like that. Soil surveys are really good in some areas and not so good in other areas. It's just the way the animal is.
Well, I worked on soil survey, doing veg stuff in the early 80s up through the late 80s and continued to work in the 90s. And one thing I found was that soil scientists tend to use every clue they can find to try to map soils, and they use existing vegetation in a lot of cases
as a guide to draw the lines.
As a guide to drawing the lines, and that may create issues in terms of what matches up.
The circularity, you mean, or?
Well, I mean, they've mapped the soils based on existing vegetation, which may or may not.
Oh, sure, right, yeah.
Your potential, and so you may not get as good a map as you would hope.
Right, and
especially in that
area. It's not a complete science matching ESDs to the soil mappings because there is that kind of what was there before all this was here,
Yeah.
type of thing.
Is it possible, or have you tried mapping land uses as one of the layers of that to try to increase the predictability of?
Not land uses, but land cover we have. And land use in this case would be agriculture versus rangeland versus forest land, and versus riparian. I'm not sure what else we have out there. Urban, we didn't do that. We just used a land cover map. Lisa.
In response to Leslie's question, just another layer that would be helpful is having the land use history map and looking at trajectories of the big transition model that we're looking at. We're looking at historic plant climate, but then where it's going, state transition model, so for data layers and things like that.
Yeah. Getting at that pre-settlement vegetation is pretty tough. There are data sets available, but they're pretty scarce. The survey data is available in the late 1800s, but still is settlement before then. There's another question here.
For the current vegetation, you did use geology too? Is that
Current vegetation, we just use, we mostly use the satellite imagery and topographic variables.
When we did this in Nevada, not what you're doing with interpreting the uniting with this, I don't know where to start. It was unbelievable how much the color of the dirt, the soil, just, we had ecological sites that were identical, and you just walk for 5 miles, and every 100 feet it goes from red to black to white to brown to, but it's all the same vegetation. But the imagery shows up as totally different.
Right, and it could be a different ESD because the soils are different.
Yes.
For whatever reason.
Yeah. And I was wondering if that was part of the noise you're seeing.
It could be because bare ground has a big impact on a lot of this. And soil color, how moist it is, whether you had a rainfall yesterday or not, and if it's a sandy soil or clay soil, the color will be slightly different depending on the moisture content.
The person I was working with told me the Landsat 7 is very good. It was first introduced for mineralogy, apparently.
Well, the middle infrared is there to look at mineralogy, but you can use it to look at variations.
Oh, yeah, but he says, he told me, don't be surprised if you're seeing all this effect of bedrock and soil.
Oh, yeah.
It's really good.
Because we can see the stuff. You know?
Yeah.
If we're in the East Coast, you know, no bare ground hardly. Well, maybe not. Anybody else?
We've probably come up to the time, so if you could give your thing to Dave, I'll explain who Dave is.
So our next speaker